Yes.
I am. Okay, thank you. So this time it seems that everything will work. So this is lecture 3 and it will be mostly on Hardy fields. Last time the main thing we did was construct the real closure HRC of a Hausdorff field, capital H. And I want to say a few things why we go into Hausdorff fields. It's partly as a kind of preparation for Hardy fields and a baby version of it, because we don't have to worry about the derivation, but also because they will actually appear as intermediate stages in certain constructions of Hardy fields. So it will, what we did will really be used. And there is also one more item that I want to cover in the Hausdorff field setting, because it will be used later on in certain arguments about Hardy fields. And so this is about the eventual behavior of a Hausdorff field H of elements in a Hausdorff field with respect to semi-algebraic sets and functions. I mean, this will really, so to say, put the real closure of a Hausdorff field on the map, because it will basically tell you why this real closure is so useful. Basically, what having a real closure means is that you can substitute in a semi-algebraic function any germs of a Hausdorff field, and you get then a germ which lies in the real closure of that Hausdorff field. So this is, but it's more precise than that. So but it's important here that the Hausdorff field that we consider contains the real numbers, contains all the real numbers, right? So let n germs be given, h1 and 2, hn, and let also a semi-algebraic set S in Rn be given. And then for big T, you can set ht equal to h1t up to hnt, right? Which is a point in Rn. Of course, this only makes sense for big T once you pick certain representatives of these germs, and we tacitly do that always in and it doesn't matter for the statement that follows which representatives you take. Okay, and then the first claim that we want to make is that eventually this point will lie in S, or it will be eventually outside of S. So what's my pen doesn't, what?
You've selected the erase.
You're right, sorry, I won. Either HT will be in S eventually, or HT will be, so it will eventually enter S and stay there, or it will get out of S and never come back, if you want to put it that way. And well, actually, let me put an N there because the statement depends on N. But of course, we are going to prove this by induction on N. The second, and the induction involves also the following. If HT, in the first alternative, if HT is eventually an S, and you have a semi-algebraic function on S, then you can plug in the H in Fe and semi-algebraic. Yeah, so here I'm using a little, I assume people know about semi-algebraic sets and semi-algebraic functions. Which is in some sense part of O minimality. right? Phi is semi-algebraic, and then you can plug in H in Phi, and you get a germ in the real closure of H. Then Phi composed with H is in the real closure of your Hausdorff field, yeah. And of course, where Phi composed with H has the natural meaning that for big T, it's equal to Phi of HT. For big T. Yeah, so I hope that the statement of this is clear, and that you visualize what's happening here. Either H will eventually stay in S, or it will eventually exit S and never come back. And you can compose, in the first alternative, you can plug H into a semi-algebraic function on S and get, again, a germ in the real closure. And that is in some sense the real meaning of the real closure of H. Okay, now I want to only give a sketch because this is a good exercise for the students, proof sketch, but I will give you induction on N. And I like to start always with N is 0. Yeah, the case N is 0. Case N is 0 is trivial. But it actually requires already that R is a subfield of H. Yeah, the assumption that H contains R is definitely needed here. The case N is 0 is trivial. And now to make the induction work smoothly, you you start with assuming 1n, 1 sub n, yeah, and then you prove from that 2 sub n. So then obtain 2 sub n. By first proving a little lemma, proving a purely semi-algebraic lemma, and that is really an exercise in quantifier elimination for the field of real numbers, proving a purely semi-algebraic. So this is sort of the model theory component of my lecture, lemma. And it's the following lemma. So let me say exercise in QE, quantifier elimination, for my notation for the field of real numbers, or that field of real numbers is RL, right? It is, because Tarski's theorem is that this has quantifier elimination. Okay, what is the lemma? For any semi-algebraic set S in Rn, and semi-algebraic function. By the way, when I say semi-algebraic function, that means, of course, that the graph of the function is semi-algebraic. I do not assume that the function is continuous, although one can always reduce to that case, but by O minimality. And semi-algebraic function phi from S to R. You can sort of split it up into S into parts. there are semi-algebraic sets S1 to Sm, finitely many, and polynomials P1 up to Pm, the same number. They are polynomials in n+1 variables in R, capital X, Y. Capital X is n variables, and Y is always one variable, such that, well, S is simply the union, right? You can make it disjoint, it doesn't matter, a disjoint union, but and you can even take the sets Sm1 up to Sm very special, like semi-algebraic cells, but it doesn't really matter for how we use this. So S is covered by finitely many semi-algebraic sets, and such that on each of those, the function phi is a root, so to say, of the equation pi x y is 0. But I have to be a little bit more precise here, and for all x in Si, two things. Pi, the ith polynomial, will be, if I plug in a point from Si for the x variables, I get a non-zero polynomial. That's important. And Pi x comma phi x is 0. In other words, the phi solves the equation Pi x y is 0, and here I is 1. Right, so that's a purely semi-algebraic lemma, and it's really an exercise in using quantifier elimination, and it's a good one for students to do. Okay, but that's okay. So once you assume 1n, you get 2n by using this lemma. And once you have 2n, you prove 1n plus 1. So next proof 1. And this is a bit typical for a lot of things in O minimal proofs, that you set up the induction in this way with two parts, where you go from something about sets to something about functions, and then you use that to go to the next dimension for sets. Next proof 1n plus 1 using 1n and 1 and 2n. And also reduction to the case where S is a semi-algebraic cell. That's also n reduction. Yeah, for the reduction to the case where S is a cell. Okay, so that is my sketch, and I leave it to the students to carry this out. And with these indications, I don't think it should be too hard. So we'll definitely use this later on in solving certain kinds of differential equations over Hardy fields as a lemma. And so now I can finally start with the real topic of my course, which is Hardy fields. So that's section 2. Yeah. interrupt me if you want. And for now, this is just the beginnings, right? This is just a very basic theory of Hardy fields. And I want to mention a few original sources for this whole topic, especially for the topics in this section. Original sources. Well, of course we should Hardy, not surprisingly. He tried to make sense of what Dubois-Reymond had claimed, which was not a trivial thing to do. Properties of logarithmic exponential functions. Proceedings of the London Math Society in 1911, 54 to 90. And then he later, there are other papers he wrote, but let me mention also his little book, which is really nice to read, Orders of Infinity. So that is a little booklet, still nice to consult. And well, let me mention just the second edition. It's a Cambridge University Press, 1924. There was an earlier edition. And then formally the notion of Hardy field was really came a lot later, namely as an appendix in a book by Bourbaki in one of the volumes. Upon these two, the volume, function, une variable. Of course, these are also available now in English, but real. 1976. So there, the notion of a Hardy field, as I define it later on, was formally introduced, and some pretty basic facts were proved about it, which we will cover today, I hope, I think. And then, well, then there are two people who really took this subject to heart. So let me say many papers by Rosenlicht and Bojanitsand in the papers by actually I think the actual definition of a Hardy field was probably in the 50s already, in an earlier version of the book, because there were also some papers by other people, like including Abram Robinson, who published in the meantime. But the people who really took this to heart were Rosenlicht and Bojanitsand, which I'm not all going to mention. I'm just and this was basically in the time from 1980 to 19 96. Yeah. If you look at their list of papers on this topic, both of them go basically from in that time. Okay, so that is what I want to say about the sources. And now I can start with the definition and some immediate consequences. And consequences. Well, 211. Yeah, well, let's fix the derivation on the germs of the C1 functions, right? If you have a C1 germ and you take the derivative, you get just a continuous germ. And this is the derivation, the usual one, which sends f, a germ f, to its derivative. And yeah, that is a derivation simply means that it's additive and satisfies the product rule, or the Leibniz rule. And then the Hardy field is simply a subfield of C1 which is closed under this derivation. A Hardy field is a subfield, a subring which happens to be a field. Yeah. C1 such that it's closed under this derivation, but then you immediately notice that then of course the derivative of an element on capital H, oh, I should give it a name, capital H, yeah. Yeah, so it's in particular also a Hausdorff field, of course. Yeah, so for an element little h in big H, the derivative of little h is also in H and therefore is also a C1. And that means the original germ must actually have been C2 and so on. So, note that then H is actually in Cn for all n, for all n, i.e. H is contained in the intersection of all these Cn's, yeah, which is by definition the intersection overall and Cn. Yeah. So that is actually a differential ring. Yeah, the subring is closed under delta, and we consider, and so we consider this as a differential ring. In other words, a ring together with a derivation on it, which maps it to itself. And H accordingly as a differential subfield. As a differential subfield. In other words, the derivation is now one of the primitive operations that we consider H as equipped with, as a differential subfield of C. Yeah, and of course, it's also still an ordered, being a Hausdorff field, a Hardy field is in particular also an ordered field and a valued field, and all these extra structures are going to interact, as we will see. So let me, the usual examples that I mentioned in connection with Hausdorff fields are actually Hardy fields, right? 2 and 2, Q. There are rather trivial examples of Hardy fields, but if you take the field of rational functions in X, right, where if we identify a rational function simply with the germ at plus infinity of the that it defines, but also if you take any O minimal expansion I don't know, this will perhaps come up in the O minimal course for any, where one shows that definable functions are eventually differentiable. And then, of course, the derivative will also be definable. And so that will make this a Hardy field. Expansion of tilde of RL, yeah, field of, or the field of real numbers. Yeah, I should have inserted here the word examples. Okay, and so till further notice, H will now be a Hardy field. Now, before it was a Hausdorff field, but now we have this extra item, namely the derivation. Further. And these are much richer in many ways than Hausdorff fields, which note that H is a Hardy field. Good. So the first thing to realize as a consequence of having this derivative available is that that for a germ in H, one of three things happens. Yeah, one of three things. First of all, its derivative could be negative. Yeah, H being an ordered field, its derivative could be negative in this field. That means eventually the function, a representative of the function will be, its derivative will be negative. So that means that f is eventually strictly decreasing. Yeah? F eventually. Again, we tacitly replace f now by a representative, and that will mean that then this representative will be eventually strictly decreasing. To f prime equals 0, f eventually constant, and third possibility is that f prime is positive, and that will mean that f is eventually strictly increasing. Right. And by the way, I should mention that this is not the case for a Hausdorff field. If you have an f in a Hausdorff field, then ft will certainly go to a limit as t goes to plus infinity, but it might approach this limit in a sort of oscillating way. For example, if you start with, well, anyway, those who tried the earlier exercises will have realized that already. So, so this is definitely something that where you really need Hardy fields rather than Hausdorff fields. Right. Okay. Now this already has. Let me mention some consequences of that. Immediate consequences. If f is bigger than every natural number, then of course. Yeah. So this is. This shows that the derivation is how shall I say, interacts with the ordering. If f is bigger than every natural number or bigger than every constant in the field, to express it in a more definable way, then that means that that can only happen if f prime is positive. Right? F must be eventually increasing, because otherwise, if it's constant or strictly increasing, it will eventually be below a natural number. Right? So this is the connection between the ordering and the derivation. If you right, and the if f is bounded, yeah, f dominated by 1, then, well, then it must go to a limit, a real number, as there must be a real number c, such that ft has limit c. And if you then subtract that limit from f, you get something that's where the limit is 0. So that means that f minus c is strictly dominated by 1, or little o of 1 if you like, for some c in R. And well, maybe you will recognize here the properties of an H field as I defined it in my workshop lecture. Let me mention as a consequence that if R is contained in H, then the valuation ring, the ring of bounded elements, must be indeed a bounded element is always a real number plus an infinitesimal element, right? That is basically what this implication here says. And that was one of the actions for H fields, if you like. And the third thing I want to mention, if f is infinitesimal, right, ft goes to 0 as t goes to infinity, then the derivative must be also infinitesimal. I leave that as an exercise. I mean, it's not a consequence formally of the previous facts. I mean, not of the itemized things here. But of course, if you just thinking about the behavior of differentiable functions, you should be able to easily see that. Right. Okay. Now some more consequences. Because of our work on Hausdorff fields, these will now have rather short proofs. Yeah, consequences. Of facts we proved about Hausdorff field. Facts about Hausdorff fields that we already established. One. Yeah, so if you take the real closure of a Hardy field, then it's not just a Hausdorff field, but it's actually also a Hardy field again. Right, 2. You can always adjoin any real number to a Hardy field, not to a Hausdorff field, but to a Hardy field. Any R in R, any real number generates a Hardy field. HR over H. Again, this is not true for Hausdorff fields. If you as those who did the exercises from last time will know. And third, yes, this is this thing about adding antiderivatives. Any f in C1, yeah, any continuously differentiable germ whose derivative is in H. Yeah, in other words, f is an antiderivative of an element in capital H. Then you can join f to H. Generates a Hardy field. H. Okay. And proof. And for, let me see, 1. Well, first of all, since H is every element in H is n times differentiable for every n, and then we already know from what we said about Hausdorff fields that this will be true also for the real closure. So will be n times differentiable also for every n. Yes, so that uses just what we said about. And but now we have to show in addition that the derivative of an element in this real closure is again in the real closure. And there we use this formula that I made explicit last time for y in the real closure with minimum, and then of course it has a minimum polynomial over H. P capital Y. We saw last time that we had Y prime equals minus P, well, let me use this notation, Y divided by the partial derivative which is an element of, again, of H, the Hardy field generated, well, by the Hausdorff field generated, yeah, anyway, this is in HRC. And here P delta is simply the polynomial you obtain by replacing each coefficient by its derivative, right? Where for if P is the sum of the AI y to the I, and P delta is the sum of the AI prime. Yeah. So you replace every of the coefficients. Yeah. Right. Of course, this delta has nothing to do, the delta here in P delta has nothing to do with the delta in the partial, in the notation for the partial derivative. This partial derivative is a formal derivative with respect to the capital Y variable, and right. Okay. Right. So that I think shows you one, and two. That was about adjoining a real number, and now we actually use that. We can assume H is real closed, right? Can assume by passing to the real closure of H, which we now know is a Hardy field. And then there are two possibilities. Either the real number that you want to adjoin is already in capital H, or not. Yeah. So, and suppose if R in H, you're done. Suppose R not in H. Well, then it's transcendental, right? I mean, H is real closed. It means it's almost algebraic closed. You get the algebraic closure by adjoining I, and so R could R couldn't be algebraic over H, so it's transcendental. Over H, and then we had this criterion for when we could adjoin it to a Hausdorff field. You have to check that R minus any element in capital H is either eventually positive or eventually negative. And yeah, and H and H. Well, what you really want to know is that the difference is a unit in curly C, but that means here R is, or R is bigger than, yeah, and why does R is eventually less than H, or if R is eventually bigger than H? Why is this so? Well, H as t goes to infinity must approach a limit. If it approaches a limit which is different from R, then this is certainly clear. And if the limit happens to be R, it could either approach it from above or from below, or it it cannot oscillate around R, right? That is so this is definitely the case. And so then we are done. Right. So now use this lemma about adjoining transcendental germs. Yeah, now use lemma 1. It was lemma 151. Yeah, of course, you also still have to show that when you adjoin R, it's not just a Hausdorff field, but a Hardy field. But that's again very easy to see because the derivative of R is 0. And anyway, these little details I should be able to leave to you. The third one was adjoining antiderivatives, right? So for F in H, for F in C1, sorry, for F in C1 with F prime in H, 152 Ah, yes, then we already had a lemma that we can adjoin it and get a Hausdorff field. 152 gives a Hausdorff field. HF. Now clearly, since F is C1 and H is all the functions in H are C1, this is contained in C1 again. And it's easy to check. Again, these are good, fairly easy exercises for the students, that if you take the derivative of something in HF, you get again in HF. Yeah? Of course, this uses the fact that F prime, you know that F prime is in H. So HF. Hardy field. Okay. So these are rather quick consequences of, oh, I'm only, yeah, I didn't cover. I still want to mention, now I want to mention the consequences of those consequences, because consequences of those consequences. Well, okay, I call these consequences 1, 2, 3. So let me simply continue to continue with this numbering. First of all, because you can adjoin any real numbers, you can adjoin them, all of them, at the simultaneously. That is a Hardy field. R generates a Hardy field HR over H. Yeah, you just adjoin one real number after another till you have adjoined them all, and that should be clear. And that means that in practice we can always restrict our attention, for at least for the kind of problem that we are interested in, to Hardy fields that contain all the real numbers. You can also always adjoin the identity, the germ of the identity function. X generates a Hardy field HX over H. Right? Because the derivative of X is 1. In other words, X is an antiderivative of something that's already in H. 6. Now I want to adjoin the logarithm for F. The positive element, this is my notation for the positive elements in an ordered field. Log F, which makes perfect sense as a germ, generates a Hardy field H log F over H. Let me see. Okay. I will continue with various consequences on Thursday, but I think I have to stop now. So thank you.
Thank you, Lau.
Oh,
Yeah. Thank you. Thank you.
oh, thanks. By the way, no, I forgot to mention why is this so? use log f. It's an antiderivative of something that is in H, right? Sorry. It's an antiderivative of this thing in H. That's why this is true. Yeah. Okay. Good.
Thank you all.
Yeah. Thanks.